Dear attendees, for your attention, a report on a topic, modeling of a phased array antenna for data transmission in urban environment, by authors Yuri Polyanetsa, Vasil Dunets and Lilia Khvostivska. Data transmission is a process of sending and receiving signals and information between different devices or locations, such as wearable sensors, implantable devices, medical instruments, and remote servers. Data transmission can enable various applications, such as health monitoring, diagnosis, therapy, telemedicine, and biofeedback. Data transmission also faces many challenges, especially in urban environment, where the wireless channel is often crowded, noisy, and multipath-rich. Therefore, it's important to design and implement efficient and reliable antennas for data transmission. A phased array antennas (PAA) can offer many benefits for data transmission in urban environment, such as a high gain, beam steering, wide bandwidth, and small size. A PAA is a collection of antenna elements what can steer the beam direction electronically. It can achieve high gain by focusing the radiated power in a desired direction. It can steer the beam direction dynamically to track the movement or location of the transmitter or receiver. It can operate over a wide frequency range by using broadband elements or frequency scanning techniques. It can achieve a compact size by using miniaturized element or integrated circuits. Designing and implementing of PAAs for data transmission is not trivial. It requires various factors such as array elements, phase shifters, feed system. To overcome these challenges, we propose to use printed circuit board (PCB) technology for designing and implementing PAA for data transmission in urban environment. We use the phased array system toolbox in Matlab integrated development environment to design a 5x9 rectangular array of antenna elements on a printed circuit board on a R4 substrate. The geometric dimensions of a single antenna elements of the PAA are shown in the figure 1. The operating frequency is 3.7 GHz. The directivity diagram of the PAA element in a three-dimensional coordinates is shown in the figure 2. The maximum directivity is 7.2 dBi. The total size of the 5x9 rectangular antenna is 0.25 by 0.45 meters. The directivity diagram of a PAA in general in a three-dimensional coordinates is shown in a figure 4. The azimuth and cutoff directivity at 0 degrees elevation and the elevation cutoff directivity at 0 degrees azimuth for PAA are shown in figure 3. We scan the antenna beam by applying a taper for an angle of -30, 0 and a +30 degrees. On the figure 4, the antenna beam scanning by applying -3 and +3 degrees in three-dimensional coordinates are shown. We project the directional patterns of the antenna onto the terranean surface. We use the Google Maps application programming interface to obtain the terranean data and the Matlab mapping toolbox to plot the terranean map. On the figure 5, the antenna beam scanning projection onto the terranean surface by applying a taper for an angle of minus 30 degrees, 0 and plus 30 degrees respectively. We conduct a virtual experiment with 3 receivers at different locations and measure their signal strength depending on the beam scan angle. The results of the virtual experiment are shown in the table below. The results indicate what the PAA can provide strong, medium or weak signal strength to the receivers at the different beam scan angles, as shown in table number 1. The proposed approach for designing PAA using PCB technology offers several advantages over traditional design, such as integration, flexibility, and scalability. However, there are also some limitations to the proposed approaches which should be acknowledged and addressed in the future research, such as the influence of the urban environment on the antenna's performance, the cost and complexity of manufacturing metamaterials and artificial magnetic conductors. The conclusions are present on slide number 14. Thank you for your attention.